Thank you very much, Nikki. So as I said earlier, we're moving away from imaging-specific data management and sharing. And now I want to tell a bit of it as an introduction. When Canada Bioimaging started working on bioimaging data sharing, we were greatly inspired. We had the chance of meeting with the Canadian Astronomy Data Centre, and they were able to share with us what they had been doing. It was very inspiring. So our next speaker is JJ Kavelaars. JJ is head of the Canadian Astronomy Data Centre. This is an NSERC organization. It's supported by the Canadian government. And he's going to tell us about the successes of 4 decades of data management for astronomy. Welcome, JJ.
Hi, thanks for having me. It's been very interesting sitting here listening since the last few days. Raise it up a little bit. There we go. Okay. The last few days to see what's going on in bioimaging. There are an enormous number of parallels in terms of the problems and the solution spaces that are being pursued. And so I found this to be a really interesting meeting to go to, particularly reading the posters. There's some great posters out there about a lot of work that's going on in all over the world that I was really fascinated by. So, yeah, so I'm from the Canadian Astronomy Data Centre. That's our logo that was created in 1984, and we hold on to it preciously. We're funded by the National Research Council of Canada to provide data services to astronomers, initially in Canada, but actually internationally. There are roughly a dozen major data repositories in astronomy. So it's pretty easy to collaborate. There's only, we can all be in one room and talk together and come up with solutions to problems. And I have some slides, and I'm not really sure if they're completely relevant to the discussion. And so I'll be talking about some stuff and showing some slides, and sometimes they'll go together. So it's a great collaboration. We work. I'm with the NRC. I'm a research scientist. I use astronomy data for my research, and I lead this organization that provides us archive services. And we are a collaboration of researchers, developers, operations people, data scientists, all working on a daily basis together to try to make the most possible things happen for astronomy data. And we have the great privilege of being mandated by the government of Canada to do our jobs. So in order for us to stop being funded, it would require the Parliament of Canada to actually vote and cancel our operations. So it's a fantastic, I encourage you all to achieve that. Yeah, it's a great idea. And so, yeah, so we do this. This is just me highlighting the parts of the NRC Act that the Canadian Astronomy Data Centre contributes to, and I remind our funders all the time of these highlights from the actual act that formed us. So. Our mission is to provide researchers with advanced innovative data management, IT products, the kind of stuff we've been talking about here at this meeting. And we have this vision of a globally connected, interoperable, sustainable, transformative research community. Exactly the stuff that you're talking about, right? Only in astronomy as opposed to bioimaging. We're imaging different things. The science is the same. The science process is the same. So. Okay, so here's a little kind of like a oversight of some things. So we have a tabular database system. We delivered 4 million queries to users last year. We had about 40,000 users last year. There are 50,000 astronomers in the world. So essentially all astronomers use our services. We delivered about 2 petabytes of data to those users in the last year. Oh yeah, there was 47,000 users took data. 40,000 users actually tried to figure out which data they wanted first before they took it. It's a strange kind of thing. We have actually a lot of users who just basically come in every day and download a whole bunch of data. I don't know what they do with it. And our operations manager told me before I came out here, last year we had 1.2 billion accesses to data products within our system. And so this is actually something that I was listening to the discussion of, creating these aggregated metadata things, and realized that this actually goes to scale, and it goes to scale pretty quickly, right? You really need huge capacity in order to maintain this. We have about a 99.9% uptime, and we get a lot of complaints about our downtime, okay? There's people just using this service every day, and scientists who are working up to deadlines. We actually look in the calendar and try to see when there are major grant and proposal deadlines and make sure that we have a little bit of extra staff on hand to make sure that nothing goes wrong in the days before that, because we know people are crunching away trying to get the last things done. Yeah, so just some other numbers. Oh, this is actually what's stored in our archive. So currently we have about 4 petabytes of data stored in the archive. It's stored at 2 locations. We follow a philosophy called 3-2-1, which is 3 copies of the data on 2 different media with 1 copy at a different location from the other 2. This is a really easy thing to tell your funding agencies. It's a recognized data standard, 3-2-1. It sticks in their minds, they understand it. And so we have these 22 million files that are delivering these data products to people. And we archive data from 28 different facilities. So we are an aggregator, that thing you were talking about, right? We're aggregating the data together in one location. We bring it all into a common metadata model, and everybody can find the observations, the astronomy data they want in that way. This was great up until about 4 years ago. Our plan now is to grow the archive from 4 petabytes today to 70 petabytes by the end of 2030. So over the next 5 years, we will double in capacity each year till we hit roughly 70 petabytes of capacity. That is because the astronomy landscape has transformed. There's a new telescope being built called the SKA. SKA used to stand for Square Kilometer Array. Now it just stands for SKA. It was SKA, then it was SKA Phase 1, and they said, oh, we'll just call this SKA. So it's not quite as big as they had hoped, but it is an enormous telescope being built in Australia and South Africa on 2 continents, connecting together data streams. It delivers multiple petabytes of data a day. So not over its lifetime, not over a year, 2 petabytes every night streaming off this facility, which will begin operations in 2027. And Canada has agreed to archive and maintain a copy of 6% of the data. So, and there will be archives around the world that will store various components of that data set. That's why we're ramping up our capacity. We also have the Large Synoptic Survey Telescope, which is another facility that will transform the data volume. That's going to generate over its lifetime about 10 petabytes of data. So, and then this is just a graph that kind of points out this thing about how things are going. So this is unique. We also operate a cloud computing platform just for Canadian astronomers. There are 120 Canadian professional astronomers. Okay, so this is how many of them are logged into our system on a daily basis. It starts from March of last year till March of this year. So basically they all log in every day. And you can see this drop around the January 1st, basically. Because it's Christmas, right? Everyone's gone home for the holidays. So, and then it just ramps right back up again. And then we have a few spots where there's that green dot on September of 2024. That was us. But we went offline and immediately started getting phone calls from people. So, and I think there are patterns in there that go with various things. So, yeah. And so we executed about 2.5 million or 2.9 million jobs for the users. This is just talking about that growth that I mentioned before. Really, it's a sustainable growth concept. Because we're funded by the National Research Council, we have actually a funding envelope that will allow us to do this and continue to operate this. So our 6% will be paired with about 12 other data centers around the world, and we'll be interchanging data between us, sharing the metadata, sharing the files, and providing compute access at our institutions for the world community of astronomers. So if you're an astronomer anywhere in the world and you want to access the piece of data that we're holding, you will log into our systems and do your analysis there. And this is, I was quite taken by the presentation that talked about the development in India, and they were using the computing VMs in Kobe, Japan. This is very much the model we're looking at, where we put the compute where the data is, and any astronomer in the world can access that compute, and we all do this kind of fair share. So, yeah, so it's going to grow quite a bit. And I think I have one more. Oops, I seem to have lost my advance. Okay, so this has been achieved through these large partnerships. And one of the things that you were talking about, and I it's like, so it's just like some secret, or not so secret, but some fundamental things you need to do, right? One is agree on a standard for metadata. Just do it. Give up your own ideas. All get together and agree and just say, okay, that's it. We're just going to use this model. And you're not going to like it because it's not going to be perfect, but everyone using the same one will enable so much power. Astronomers have done that. I can look for data at any of the 12 data centers using the exact same information, and then agree on a data delivery standard, how files are delivered from one place to another. And once you have those two things, you have this interoperable network of all these great imaging data sets. So I think those are the two things to take away from and to do. So thanks for your time.
So we should thank again our speakers, and now we're going to open the floor to a panel discussion in which I hope there's going to be a lot of questions. If nobody has questions from the floor, no worries. Judith and I have plenty of questions. So please, let's start from the floor. Please.
Hello. Hello. Hi. It's for Natalie. This sad thing happened to me. So we submitted a paper, and reviewer 2 said, oh, you know, you need to do a whole bunch more experiments. And then we were like, wait a minute, the Allen Institute has this data already, so we went there and we downloaded it all and we plotted it all and visualized it, and it showed exactly, and it was like so nice, like completely independent validation of the thing that we found, separate method, put it in the paper, made the figure, resubmitted, and it said, reviewer 2. I will say that the quality and rigor of the Allen Institute's connectivity data make it perfectly suitable for an initial screen, but wholly inadequate for independent publication without further validation. Discuss.
Is this on?
It's not on. Yeah, I don't want to talk about it. No, but I mean, you know, I was really pleased with myself that I thought to go to the online repository, that we went in and we used the data, and reusing the data, you know, and particularly, you know, I have to say the Allen Institute data sets are just the best, right? But what do we do if the reviewers are going to push back and go, oh yeah, well, but you know, you have to also repeat all those experiments again? Like, what's the point?
Well, yeah, I think this is like a mindset that needs to be changed. It's not going to happen in one day. But I think it's a mindset that we need to change, obviously. It costs a lot of money to reproduce experiment, you know, raw data like that. And we need to start thinking of being a bit more sustainable and be able to do exactly what you did, which I applaud. That's what we should do. And I'm very sorry for the reply from reviewer 2. Anyone else?
I just want to remind people to introduce themselves briefly before they ask their questions.
So it's interesting because in astronomy, we've gone through exactly this kind of phrasing from reviewers, where, well, that was great, but you know, what is the quality of that data? How was it acquired? And so we've started producing really extensive characterizations and quality control papers that go with the data sets. They don't describe any of the science. They just describe how the data is acquired, how you used it. And after about 10 years of doing that, the reviewers have stopped asking that question. But it only took a decade. So.
Hi, Beth Simini from the Broad Institute. my question was a little bit for you, but sort of for the whole panel. Global data is great, and all of this is great. Who pays, and how do we convince the government, like, to pay for things where it's like, well, you made that data in collaboration between 2 different countries, you know? Some of that data was made in the US and some of it in Canada. Why should US pay for it? Why should Canada pay for it? How do we do that gracefully?
The question was for a specific person, or?
Anybody. I was specifically thinking about the astronomy use case, because you were saying people can come and process their data, you know, on your stuff.
Right, so astronomy has an open skies policy that the astronomers decided on, and so we share data internationally uniformly. Every astronomy facility does this. They often provide very short periods of closed data access, and then immediately your data has to become publicly accessible. And because it's all publicly accessible, that makes it really easy for the research funders to say, oh, yeah, we'll happily provide you funding to make your open data more accessible by large communities. They don't want to make your closed data more accessible. That doesn't make sense from a funder's perspective. However, even that, I have had my vice president say to me, why don't we charge per download? And we have to go, and that's usually a new vice president comes in and they ask that question because they see what the rates are like, and you have to explain the whole open skies concept over again, and that, you know, there are 12 data centers. Do you want Canadians paying fees at the other 11, or do you just want to participate in this open network? So.
We're going to have a question from the online audience. For Natalie, how does BFF plan on dealing with structured metadata or metadata that doesn't conform to an open file model? It's written there, but yes, open file, or pair file, so for a pair file model, sorry.
If I may answer that one, actually.
Go for it.
and feel free to talk to me for BFF later. But BFF already works with non-structured metadata, or data that don't conform as a pair file model with an accessory CSV. It's a little bit technical, but it's actually, I just did that for someone who emailed me this morning, and I did it in 5 minutes. So we have a forum, and you can ask questions on the forum if you just go to bff.allencell.org.
Yeah, that's well said. You know, it's an open source thing. We're open to receive requests. If you want to use it, tell us what's missing. We will work on it.
All right. So,
Hi, David Joy from Denali Therapeutics in San Francisco. So I'm an image analyst. So I take your microscope images and I scribble on them. And sometimes those scribbles are made by open source code that I can just happily upload to the repository, and it's great and definitely bug-free, and that's good. But my users like to use closed source platforms that do question mark and produce analysis through 50 steps that I don't know what's going on, and sometimes the manufacturers won't even tell me. So do you have thoughts about, one, what kind of analytical artifacts we should be uploading so that people can reproduce my stats and hopefully get the same figure? And then two, what kinds of analytical metadata we should be depositing into these things, especially from closed source platforms?
Yeah, so that's true. So we are discussing about how to kind of share the metadata for the analytical process, and also the most importantly, the sample itself and how the sample is treated. That is a very important information, but it's not difficult to handle. So that's what we are discussing about that. That's, so at least in SSBD, BIA discussion, ideal discussion. So we are working on it. That's that's
okay, on this side?
no help. Good. Sorry.
It's a hard problem.
Okay, so.
Great. First, I want to thank the organizer because inviting an astrophysicist is amazing. And I love this concept of like, they figured out the metadata problem, and I sometimes feel ashamed as for our community not having done it. And I just want to say, like, the art community, research on art community did the same. You can download on the Getty data a thesaurus of 50,000 metadata column with their definitions that the field agree upon. And I think next time we should have also someone from that community. But my question is, if you make this like data set accessible online akin to an archive since 1984, more classical archive have a life cycle of data. And at some point, you don't keep all the data. And after 10 years, some data is eliminated, 25 years. What constitutes a data that you could eliminate? Because you're not going to keep 60 petabyte every year accumulating. And how do you deal with that one researcher that it was their most favorite data?
That was what? Most favorite data.
Yeah, so there's two answers, and they're kind of in conflict with each other. The process that we have is files become cold, and as they become cold, they move to near-line storage instead of online storage. Any researcher can keep a file hot. It's a very simple process, and it will stay online. But you know, there's a limit to how many files a person would do that for. The cold storage or the nearline storage is tape accessible, and it just takes a bit longer to get to. We've never thrown any data out. I mean, after 40 years of operation, what we've learned is the other side of the thing, which is that as fast as your brain thinks you're hitting a limit of how much data you can store more data. Like, it just is, you know, the scaling of Moore's law is actually pacing along really well on the storage front. And growing capacity for storage is the cheapest way to do more science, right? You can reuse that data to solve another problem or to confirm another analysis. And that is so cheap. You know, spend $100 million on storage. It is extraordinarily cheap compared to building a new research project and reacquiring all that information. So, yeah.
Thank you for that.
The Digital Research Alliance of Canada thinks the same, right?
Okay, next question from that side.
Hi, I'm Uri Manor from University of California, San Diego. We do a lot of imaging research. We also do a lot of deep learning development, and have always been really excited to see people advocating for more open science, sharing of data, so that we can train ever better deep learning models. So I want to connect JJ and Nikki's talks. So Nikki had that pyramid. I think it was your talk, right? With the pyramid, and at the very top, make it required. Just underneath that, I think it was make it rewarding to share the data. And I think that's the really key thing, is that the reward has to overcome the cost of sharing your data. And I think we can learn a lot from the social media companies, where people willingly share everything, their innermost thoughts, to whatever they shouldn't be sharing also. But the point is that if you make it rewarding for people to upload their imaging data, then people will do it automatically. You don't have to tell them to do it. You'll be dumb for not doing it, right? And so I want to connect that to JJ's point about we all need to agree on a common language and standard for our files. I think that's easy if it's telescopes. I've always been jealous of the physicists where they all use the same telescope. Yes. And it's one, you can count the number of telescopes on the planet. I can't even get my lab to, like individual members of my lab, to use the exact same metadata formats. All right? I had fantasized about it, about like having a tutorial and everyone would use the exact same style so that we could build our bigger models. It doesn't work. But what I was thinking was that you're in a good position, especially Nikki, I think. Hire a large language model engineer to be able to look at all the different metadatas and translate them into whatever common metadata you need, so that we can do whatever the heck we want, and your model figures out how to make it compatible. Is that realistic? And that's it.
I think he gave me an impossible question to answer, but I'll I'll give it a try. And actually, JJ and I were talking before coming and presenting, and we were just realizing that across Gray, we did the same kind of mapping that you did and looked at the different standards across the generalist repositories and learned that we all used DataCite. We all had common metadata that we were using that was roughly the same, and a little bit of tweaking to bring that to a standard we could all share. And JJ was mentioning that that's sort of the lowest denominator as well that they're using. So presumably there is some common metadata that is already at play that could start this ball rolling, and then we can expand over time to find ways to use models to help us inform what the additional metadata that can translate across could be.
The astronomers do realize that it's a very particular field that has a kind of like so simple problem to solve, and so was able to solve it. We do get the thing where every year we have a data meeting, and someone will come and say, I have an idea for a new file format. And we basically just beat them to death.
Okay.
Okay, Hilmar Strickvan from Faculty of Medicine and Dentistry in Edmonton. I'm extremely thankful that we have this discussion here because computation becomes more and more important in microscopy. As now, you know, like microscopy is like computer science for specialized hardware. So we have to, our users are usually not able to store their stuff even if it's mandatory for a certain amount of time. And I think it would be good to centralize these things, to outsource this. We have now very good ties with IST, and it should be mandatory for the granting agencies as well to allocate a certain amount of money for the storage, because, you know, I like the Amero project very much. You can probably keep this for the researcher for a certain amount of time, then you open it up for other labs in the country and then worldwide, so that it can be reanalyzed and the data can be used a lot of times. And then the other point is about the metadata. I think we need a more flexible approach, like what my colleague said before. We probably have to automatically tag these and annotate these pictures, and then have flexible databases that are even going beyond the scope of imaging. We have a lot of metadata for sequences, for these kind of we have to go more multimodal. And if we are only comprising it to imaging, then probably we are losing a lot of synergy.
Mm-hmm. Any comments? I don't know if there was a question. So.
Okay. Just like, that's my thoughts.
Okay, just the thoughts. Okay. So this side?
Hi, my name's Kathy Galbraith. I'm from Oregon Health Sciences University. I just want to throw out an idea of how you, in your dream world, would this be possible? So some journals are now, basically, if you submit what you're going to do, if they approve that, and then you actually execute exactly what you said, they will then accept it. So then you have now data that's collected in a way that's already been pre-approved, which would eliminate some of the questions that Elizabeth faced. So how in your dream world could you see integrating like what Claire's proposed and having people really well trained to having data collected in a pre-authorized, curated manner to having then the metadata that you really want? So in your dream world, how would this possibly ever work?
Anybody want to answer?
So in planetary science, they have a similar thing where you have to describe how your data will be made public and accessible when you apply for the grant to acquire the data. And if you do not close the cycle, you do not receive your final installment of your grant. And basically, planetary scientists publish 100% of their data in open formats with correct documentation, and it's curated and vetted before it's allowed out. So it's a move towards that kind of perfect world where you say, oh, okay, I'm actually being paid to make my data accessible and usable at the end of my experiment. And I don't, it's basically a fundamental thing, right? We have jobs and we do work, and if we're not going to be paid to do something, it's very difficult to do that thing.
But I think my understanding is that a lot of the data that is collected with planetary science is kind of standardized how it's collected because there are fewer places to collect it, whereas for biological data, it's kind of collected in very different standards and all over the place.
Yeah.
To follow up on this, when we did the reproducibility project, we did prepare a pre-registration report, Nikki. So would that is still in place at the COS?
Oh yeah, I think what we're talking about is the registered reports model that a lot of journals have adopted, that exactly as described. And then as JJ mentioned, we've also run several initiatives where we've connected that with the funding. So again, it's aligning some of the incentives with the outcomes we're shooting for, and so far we see a lot of positive results from that type of work.
Yeah. Yeah. Okay. Actually, I'm going to give her the floor because.
Thank you, everyone, for your wonderful talks today. One topic that previously came up in our meeting is related to sustainability and being green when talking about bioimaging. For these data centers and these repositories, are you guys currently taking any steps to be more, more green, or thinking about this for the future when we think about, 2035?
Green computing?
I can take that. I can try to start with. I think that what we're proposing is very green, to stop collecting data crazy for no good reason and look what's out there. And if you can find it and reuse it, start with that. Having a centralized metadata catalog will also prevent you from duplicating a lot of the image data, which takes a lot of space and it's not so green as well. Yeah.
Yeah, should be related to that. So we should kind of reduce the number of the computer resources in the nationwide. So, and it's also reduce the electric power cost or something like that. That is in total going to green as well. So, and also the reduce number of the animal to kill or reduce number of the people to work. So that is also green. So that's a yeah, I think that's going green associated with that.
Thank you so much.
Okay, quick question for JJ. So when you get to petabyte level data sets, right, you're no longer in a mode where people can download it and work on it, right? And so we've sort of gone through the same thought process, and your conclusion is, you have to provide compute where the data is, which makes perfect sense. But you already have users that randomly download stuff every day without even looking at it. So how are you planning on sort of regulating that access to compute and prioritizing it? Because we've thought about this as well, and I'm just really curious to know how you plan to do that.
So, yeah, that is a problem. And in fact, I can give you lots of anecdotes of users who come into our system and grind it to a halt because they're doing something that is just not a very intelligent thing to have done. And then we just do user education with those particular individuals who are doing that, and try to use community pressure, essentially. Because astronomy is really a very small community of individuals, right? There's 50,000 people, so you're not really more than one connected point away from anybody. So there's lots of social pressure that's used to achieve that. And then, of course, computing cycles are allocated. So once you've used your computing cycles, it doesn't matter that, that's it, you're done until the next allocation round occurs. But the network is the problem. So we don't restrict you. You get an allocation of 1,000 compute cycles, or 1,000 cores of computing. We don't say you can't retrieve the entire 4 petabytes of the archive doing something. We don't know what you're doing. So this creates these huge network bottlenecks, and then we just go to directly interacting with those users to get them to not behave in that way and try to figure out what problem you're trying to solve, because there's probably a better solution. So we have actually 3 scientists who spend most of their time interacting with users, trying to help them find more effective ways of doing the analysis that they're doing in order to remove those burdens. But those burdens come, and I don't think we'll ever get rid of them completely, so yeah.
It's just worth thinking about with all the stuff about the cloud and everything else, and cloud compute's costing all this money, that once we have the big data repositories, a way to get the compute at the data is going to be really key, and it's
and data centers get clogged. The clogged up network in our data center is our biggest user complaint.
Hi, my name is Chloe Van Osten-Triplet. I'm working at University of Ottawa, and it's still in the same area, but I'm going to step back, and I like to go on the ground. Most of the labs that are funded all over the world, and I think it's one of actually a slide that I like from Katerina. You know this mountain of hard disk that are piled up in the PI's office, or the lack of reproducibility from even one lab, from one PhD student to the next PhD student or the next postdoc. Nobody will go back to this hard disk that is now 10 years on the shelf. Even a postdoc will never trust even the data from the PhD student from previous year. So even well-trained students, we would train them on instruments, on confocals, let's say. I would go to the basics for it. And they are going to acquire completely differently. I see PIs, because they have learned to use confocal in a certain way, cranking the gain, averaging 12 times, just to have a better signal-to-noise ratio, etc. I know that right now you are looking more at making sure that the metadata are usable. But what about the quality of the image? So even before that, how can we make sure that in all those data centers, and even, so let's say that all the metadata, you figure it out, we have only one type of metadata. How can we make sure that we are going to use those images? How can we make sure of the reproducibility of this huge data? I was just wondering, who is going to use all these images at one point? Like from all the labs that, for example, I am working with personally, they are never going to I will even not trust their images to be part of those repositories. How can we make sure that all those data centers do not have a lot of craps?
That's a bottom-line question.
Thank you. I can start with this, if that's okay. I'm sure a lot of you are thinking about this right now, so Chloe's right on it. The only thing I can say is the short answer is metadata. So if there's no metadata, doesn't matter what the quality of the image is. It's very difficult to trust it. And I have some little anecdote I can tell you at the poster later. Come see me, I'll give you tons of examples. So metadata is key. It's hard to do this retroactively. So that's why I was saying it's very, very critical that you collect all this metadata when you capture the images. So you capture all the context to it and you record it. And yes, we don't have like this perfect standardized model, what metadata you need to collect. So just collect everything. Mm-hmm. We'll see what we need at the end of the day. It's change of culture. It's not, yeah, it's a mindset we need to change. Hopefully soon we'll be able to tell you, don't bother with this, don't bother with that. This is what we need, but we're just not there yet. We need to see what can be collected. That's my best advice to everyone on that front.
And I just want to make a comment. Right, go ahead. And I'll make a comment.
Yeah, that's metadata is very important. I agree. That's about so in Japan. So we propose recommended metadata to keep and deposit into our database, but many people don't want to use it or don't want to follow it because it's laborious. So we are taking two different approaches. The first one is working with the facility. So the facility people is more systematic, and they are very much professional to keep every track of the experiment. So so in RIKEN we have many kind of imaging-based facility. So we are working with them to making a system to assist their taking the metadata by using an e-notebook to put into the system, or kind of every communication between the user to be put into the e-electric kind of things. So, and also, okay, I'm moving to the different approach. That is the individual laboratory. So we are put into the some example of the individual laboratory to work with it, how to kind of systematize taking the image data with the notebook, and it's also we are put into the e-notebook system to get the good metadata out of that. So, and in total, so we on top of that, we need to get some education as well. So, but we need to do such kind of the more kind of concrete approaches to make the metadata available for the database. Other than that, it's so that's a long way to get the good one. That is our approach currently taken.
We have time for one more question, so it's going to be on that side.
Hi, Genevieve Leprade from McGill University. So we've seen several years of discussion and efforts put into ideas about standardizing metadata, but like JJ said, at some point you just need to do it and you just need to implement this. Obviously, as we said, microscopy data and bioimaging data is very, very complex. But how do we take these steps to kind of bypass this bottleneck and implement these standards and transition from just saying to doing, and who's going to be the one to do that?
I mean, I can comment for sure. So, yeah, so I mean, what Natalie was talking about was the fact that we need to build, I mean, they're already planning on building a consortium so that there is going to be some decision making done. I also want to, so I think who is going to do it is all of us. There is a lot of, so, and also I want to say, yes, there has been a lot of years building this, but you also have to think that there has been a lot of years developing all these technologies. It's not like things, so it's not like it's magical and it happens. If you want to build consensus and you want to bring people along, it takes time. And on this, I want to comment on the fact that yes, we will definitely leverage AI wherever possible, but I also want to caution about the idea of using AI to avoid talking to each other. So I think we cannot bypass talking to each other and agreeing on things. And AI is not going to solve our ability to necessity to talk to each other. So there are certain areas of metadata that we are already making strides on standardizing, like, for example, descriptions of hardware. Even though there are multiple different types of hardware, we are working in communities to do that. There are other areas in which probably scraping from papers is going to be a way of coming to an agreement on a standard. So I definitely encourage people to not think of easy solution. Yeah.
Can I make one? So yeah, that's a good point, and I agree that it's very difficult. So actually, when I back to the 2019, so we discussed about it, and it's almost impossible that it's a conclusion. So that's why we started use the wording of the harmonization rather than using the standardization. So that's we depending on your specialty or area. So that's the metadata or the kind of ideal metadata should be different, but we can make some softer connection in between. That is the kind of realistic solution. So that's why. So we are changing using the harmonization.
And then Claire has to come up.
Can I just do a little pitch?
Okay.
So I know, this is a pitch, this is a comment. So one of the things is metadata is so dry, right? It's really, really dry. So I have a poster out there and I'm trying to make metadata cool again. So please come see my poster this afternoon and help us figure out how we get on the ground level of metadata being cool, okay?
Great. Thank you so much. And I think Claire has an announcement. No, you have an announcement.
Yes, so essentially we invite you to continue this conversation over the lunch break. And quick announcements, please the poster flash talk speakers, please come in the front at the end of this session. And then Claire, you want to make an announcement? We'll do it, okay.
This is the special.
All right.
This is the special GBI.
So thank you very much to all these speakers for this nice session.